Hello everyone, I hope you're doing well. So in today's video, we are going to go through the 2024 VCE, physics exam multiple choice section. I just want to say congratulations to the class of 2024 for completing this, exam today. I heard it was easy, which is actually great to hear. Please take these with caution. These are my suggested solutions. If you see me make any silly mistakes or, please let me know. I'm making these solutions so students who've done this exam today can actually mark their paper with mine, compare their answers. And like always, guys, if you want private tutoring for physics, specialist methods, and chemistry, or have siblings, friends who want tutoring, you can always email me through this email. Let's smash through these solutions. Alright, so question 1. So Joe is standing inside a lift that is traveling vertically upwards at a constant speed. So if she's traveling at a constant speed, it means that, remember, constant means that the acceleration is 0, or the overall net force is 0. So let's take that, of 2 meters per second. As shown, Joe has a mass of 75 kilograms. Which of the following is closest to the force exerted on Joe by the lift floor? So we're basically talking about the normal force. So the floor that pushes up on Joe, basically, the normal force, N. That's what we basically want to calculate. Is that right? Which of the following is closest to the force exerted on Joe? Yep, by the floor. That's what we want. Well, let's consider all the forces. Well, we know there's a normal force. We also know that there's a force of gravity that goes downwards. Force of gravity. And basically that's it. So adding, of course, there is no acceleration, but she's going up. So we'll take, the direction of positive as up. We'll take the direction up as positive. So let's write it. The net force... We know that the net force is the total sum of all forces, which is, of course, N plus Fg. But N is positive because it's upwards, whereas Fg would be, negative. So it'll be N minus Fg. Now, we know F net is 0 is equal to N. Fg is basically Mg. So basically, Mg is equal to N. So your actual normal force, which we want to calculate, is just the force of gravity. So, mass is 75 kilograms, and G is 9.8. And that would give me what value? So, 75, 9.8, 735 newtons. Done. So, which is approximately C. Choose C for question 1. Question 2. A space-based observatory of mass m has a circular orbit radius r around the Earth. Modifications to this SBO have doubled its mass and its orbital speed is constant. Which of the following is closer to the orbital radius of the SBO after the modifications have been made? Now, if you don't know this, you remember that the mass of the smaller... So let me explain. It's a little bit more kind of confusing, but if I draw... Let's say this is the Earth. If I draw this is Earth, and let's say this here is the spacecraft here, the SBO observer. This is the radius between them. The radius, so r. Yep. And, this is the small mass. It's actually, the mass, it's called M. So I'm going to call it M. It's the mass of the SBO. And, of course, this is the, let me actually make a little m to make it more easy to understand. This is the big M, which is the mass of the Earth. Now, so we know that using this velocity formula, velocity is equal to the square root of GMR. Yep. Affecting the mass, remember that if you're doubling the mass of your SBO, it's independent on the velocity and the radius, because what only changes those values is the mass of the bigger mass, which is the Earth. If they change the mass of the bigger Earth, then you'll have some values that are changed, like the radius changes and stuff. So absolutely, there's no change. If you double the mass, if you have a bigger mass, or whatever mass you have that's orbiting, it's not going to change your overall radius. I hope that makes sense. So your basically mass of the smaller mass, which is your SBO, is independent on the radius. And that is quite obvious. I just wanted to kind of explain it with the formulas too, which makes sense. Yeah, which of the following is close to the orbital radius of the SBO after this modification has happened, which would mean it's R. So it's the same, basically, radius. Next question. 3. The diagram below shows a small ball traveling at a constant speed on a horizontal circular path while suspended from a ceiling by a string. Beautiful. Which of the following best represents the forces acting on the ball as seen from the front view, front on view? Alright, that's easy. So we know that there's always a force of gravity that pushes down. And there's also a force of tension right over here. the force of tension of the rope. Now, those are the actually only forces that are there, but, you know, of course, they add up, they create a net force that's on the right, but there's no need for the net force overall. We just want the forces that are acting on it right now, which are these two forces, which looks like A is for that one right there, so 3A. Yeah, done. Next question. Question 4. It says, the diagram below shows a 50-gram ball and a spring inside a horizontal launching tube. Assume that the launching tube is frictionless and the mass of the spring is negligible. Alright, the force versus compression graph for the spring is shown below. Consider the spring as ideal. Alright, that's perfect. The spring is initially compressed by a distance of 10 centimeters. With the ball, you know, in contact with the compressed spring, a short time later the spring is released, which of falling is closest to the speed of the ball as it leaves the tube. What a beautiful, nice question. Well, let's think about it. The ball was initially here. Oh, that's not very ugly. Come on. There it is. So the ball was initially over here. Yep. And the ball has no energy. I mean, it's stationary, nothing. But what they do is when they compress it, they're compressing the spring. So right over here, in this position over here, the actual ball over here in this position, the ball is, there's only spring potential. It has gained spring potential energy. And there's no kinetic energy. Of course, there's no GPE because it's stationary. They're holding it. So after they release the ball actually goes out, and all that spring potential energy, when it releases here, becomes kinetic energy because, absolutely, you know, speed. So there it is. And remember that, of course, the total energy is constant, so these energies here must be actually equal to each other. So your SPE is equal to kinetic energy. Well, of course, SPE is what? You know, it's half K times change in X squared equals the kinetic energy, which is half mv squared. You can actually cancel those halves out, and we get this. The K value actually can be just calculated by, you know, the gradient of this line over here. You can calculate it by the gradient, which it's just constant. So just take two. If I got it's 0 here, let's take this point over here, which is basically taking, you know, it's the K value, you know, y2 minus y1. It's just 40 over 10 times 10 to the negative 2. Remember, making sure it's in meters, which gives me 40, 10 times to the negative 2. That gives me a K constant of 400. So 400. So 400. And how much did the spring was compressed? It was compressed by 10 centimeters, which is 10 times 10 to the negative 2. Make sure you square that. The mass of the ball, which is 50 grams, I think it was. 50, you know, make sure it's in kilograms. So 50 divided by 1,000, which gives me 0.05. And velocity squared, and that's what we're calculating. Easy. So let's do that. 400, 10 times 10 to the negative 2 squared. What about that? And then take the square root of that. So our velocity I got is 8.94 meters per second, which gives me C as my answer. What was that? Question, yep, 4C. That looks good. I mean, there's also another way you can do it. Again, the spring potential energy could have done much more quicker by just finding the area under this graph, using, you know, the area of a triangle. And yeah, you could have done that. Same, you know, answer at the end of the day. Question 5, let's have a look at this. A rock is dropped from rest at the top of a cliff towards the ocean as shown below. Alright, which of the following graphs best represents the rock's total energy as it falls towards the ocean from the from the top of the cliff, ignore air resistance? A really nice question, really typical kind of easy question here. Well, let's look at the energy. Well, at the top over here, when the ball's here, all of its energy is gravitational potential energy because there's height. It's at its maximum height. And of course, the velocity is 0, so, you know, your kinetic energy is 0. Now, remember that the total energy, total energy is just the energy of the gravitational potential energy plus your kinetic energy. And remember, this value is always constant, if you're wondering. So we know that, the kinetic energy here is at its max, so the GP is max. And we know when it falls, like, let's say, when it's around here, let's say, that's where the ground is, let's say your GPE becomes 0 and your kinetic energy becomes the max. That's where the maximum speed happens. So overall, we're just waffling here. But overall, just to understand it, we know, I want to also, it's a really easy question, but I want to just go over and beyond, just try to explain the concept here. So let's say this is your energy and this is your, let's say this is your distance. Let's say this is your, distance from, like, this is from the top, this is from the bottom of the ocean or something. Okay. Now, when we're talking about, we said that the total kinetic energy is actually the total energy is always constant. Whereas, that's still total energy, T. When we're talking about, like, let's say if it was GPE, we know at the top it's at its max. It starts at max, but when it reaches the bottom, it's constantly going down. So it'll go like that. When we're talking about kinetic energy, also kinetic energy would kind of look the same, but it would look like, it would start at the top, it will be 0, but again, it will, be higher at the bottom. So it'll look like this. These are all your energies. So that's KE. Again, these are just a little bit rough sketched, not the best, but overall, just remember your total energy is always constant. So it would be A. So question 5A. Yep, so question 5A, perfect. Question 6. Two magnets are placed as shown in the diagram below. The magnets are identical and point X is exactly halfway between these two S poles, so the south poles. And yeah, straight away we know that these are gonna kind of repel, and so X has 0. It would be 0. Like there will be no magnetic field lines there, by the way. Where these field lines are coming in, by the way. Okay. Which of the following best describes the strength of the magnetic field at point X? It should be 0, yeah. It is very close to 0. And yeah, that could be true. What? It's half the magnetic field due to nope, nothing with that. It's twice the magnetic field, nope. It's about the same as the magnetic field, nothing. It's just A. It's the one here. It's very close to 0. Normally you would expect it to be 0, but yeah, it could be like 0 point something, close to 0. So the best one is A. Really nice question there. Question 7, let's have a look at this. Diagram A shows a single loop of wire carrying a current within a uniform magnetic field. Diagram B shows the same loop rotated clockwise through 90 degrees. The magnitudes of the force on the side PQ and the magnitude of the force torque on the loop in the diagram B, is FB and TB, compared to those of the diagram A. Okay, which of the following, represents, which of the following rows in the table best describes the comparison? All right. Well, you should realize that straight away. The force is constant. It doesn't change. The magnitude of the force, it's always constant. Even if it rotates, a lot of kind of students forget that the force is constant. Like even when it's, let's say when it's at this, over here, you would believe, oh, there's no force. The force is 0. No, there's still a force actually. If, there's still a force. So imagine this one's down. There's still a force. The magnitude is always constant. So the force is always constant. So like the force at A and the force at B should always be the same. So it's not B or C. But the torque is different. That's the key. The torque is different. So when we're talking about torque, at here, so at A, the torque is very, very like strong. It's really high because it wants to rotate it. It's this high torque that wants to push it down. Whereas when it's at this position, the torque is not, it's very small now. But there is still rotation. The torque is what makes it actually push, what makes it a little bit move. So here the torque at A, we know it's going to be greater than the torque at B, by the way, because again, makes sense. The torque here, there's when it's at its vertical position, the torque is really small. So D is the answer. A sounds wrong. They're not equal. I hope that makes sense. So 7D. Yep. Question 8. A straight wire P, 4 centimeters long and carrying a current of 5 amps is completely placed in a uniform magnetic field of magnitude 2 of this as shown below. Okay, beautiful. Everything looks good. Which of the following is closest to the magnitude of the force acting on the 4 centimeter long wire magnetic field? Quite easy. So we know that the force, force is equal to N current length times B. So it's a single wire. Yeah, it's a straight wire. So it's 1. The current is 5. The length of the wire is 4 centimeters, which is 4 times 10 to the negative 2 in meters. And the magnetic field is 2.0 times 10 to the power of a negative 3, which gives you times 10 to the negative 2, 2.0 times 10 to the negative 3. So which gives you basically 4.0 times 10 to the power of, so 1, 2, 3, 4, negative 4 newtons, which is like C is the answer for that one. So what is it? Question 8C. Perfect. Question 9. Two equal positive electrical charges are separated by a distance D exert a force F on each other. True. The distance is changed so that the charges now exert a force of 6F on each other. This is actually similar to the, I don't remember, is it? I think it's the Northern Hemisphere paper, 2024. Which of the following is closest to the new distance between the charges? A really nice question. So what we can do is, okay, so we know that originally the force is what? You know how it's K times Q1 times Q2, but because they're the same, it's just Q squared, basically, over R distance squared. Isn't that right? That's the force. But because we want to 6 times that force, imagine rewriting it, 6F. If I multiply 6 in front of the F, I have to multiply 6 in front of this, here, value. Now let's have a really think of what's happening here. Let me rub this part here. Okay, what I want to do is actually do this. I want to, this 6 here, I can rewrite it as 1 over 6 in terms of fractions. Like, I can write it here as 1 over 6. 1 over 6, by the way. Because, when it reciprocates, it's the same value as 6q, yep? And I want to bring it inside that distance thing. So how do I do that? Well, if I take the square root of 1 over 6, like, if I want to bring it inside, I just have to take the square root of 1 over 6 d squared. So can you see now it's inside? Yeah. So your overall, so what's your thing? So in terms of distance, what would the distance be? It would be the square root of 1 over 6. Square root of 1 over 6, which is, so it's basically this here inside, your new distance, like your overall new distance is 0.41 d, which is B as your answer. Really actually not too bad. So question 9B. All right, next question. Question 10. The graph below shows the induced current for a coil of conducting wire as a function of time, which of the following shows the magnetic field graphs corresponding to the graph of the induced current. A really nice question. So a lot of people don't get confused. Induced current, think of it as the, it's because of, it's like the same as voltage, by the way. Like, think of it as the same as voltage. Like, if I is a constant, if resistance is a constant, voltage and, current are kind of proportional. So you can, if you're wondering, like, if you're confused, just make this as a voltage graph. So imagine make it as a voltage graph. So, and yeah, when you're talking about the magnetic flux, it's really easy when you're looking at the induced voltage. So, so think of it like, okay, so you remember it's like this. So the flux diagram, just drawing it by hand, would look like this. So if that's flux and that's time. So let's think about it. Here you can see that, you remember, here there's a constant value. So it means in terms of gradient, in terms of this, it's going to be a positive, because it's positive, of course, it's above, and it's actually constant. So it's going to be some constant value like this. It's going to look like that. But now look at the next part here. It's actually higher. So, because remember the voltage is just another words for, so the induced voltage is just the gradient of this flux diagram. So here you can see that the gradient is higher and yeah, more positive. So it's more steeper. It will look like this. And then it just comes back to normal. So it will look like the old steep. It looks like this. Basically, it will look like that, which is basically C as your answer. Your ones are all wrong. Absolutely. Because this here, if you derive these will be all zeros basically, and these are all constants. There'll be zeros, and yeah, you won't get the same. Hope that makes sense. Perfect. So C. Yeah, what is it actually? Question 10C. Yeah. Let's have a look at the next question. In Victoria, the electrical energy generated by Loy Yang A power station is transmitted to Melbourne, approximately 170 kilometers away using 5 kilovolt transmission lines. Which of the following best describes the reason for the use of high voltage transmission lines of electrical energy over long distance? This is a really typical question, really easy question. Remember, we use high voltages in those transmission lines because it reduces the current. It decreases the current, and using P equals power equals I squared over R, if you reduce that current, your power loss in those transmission lines is small. That's why we actually have those high voltages in those transmission lines. Transformers can be used to increase the voltage. No, it doesn't even explain. Yeah, we're trying to explain the reason for those high voltage. High voltage reduce the energy losses in transmission line. Absolutely is the correct one. Remember, it reduces because it reduces current and hence reduces the power loss in those transmission line. C says high voltages can easily carry large power required, but nothing got to do. So these ones, high voltage reduce the overall resistance. Okay, none of them overall have explain it. So it's only B. That's a really nice one, actually. Question 12. The diagram below shows a coil moving upwards from the north pole of a stationary magnet. Okay. Which of the following correctly identifies both the direction of the induced current as observed from the top of the coil and the direction of the magnetic field produced by the induced inside of the coil as observed from the side of the coil. So this is just the application of Lenz's law. So let's think about it. So currently, if you're getting this here and putting up, you're decreasing the flux because remember, this north is actually, the field lines are passing through it. And so as you're putting it as you're pushing it upwards, you're decreasing this flux. What happens if you decrease flux in Lenz's law? There will be an induced magnetic field that will be in the same direction as your field line. So this here, this would be our induced magnetic field. It'll still be upwards. So which one's that? Induced magnetic field direction is upwards. So it's not A. and it's not D. Now, okay, now we want also the current direction. So you remember using your right hand grip pull, if you put the thumb upwards and you curl your hand, you'll see that these rotate this way. Your fingers curl this way, actually. So if you do that, your fingers curl this way, which means that if you're looking at it from this perspective, like on top, it would look like it's anti-clockwise. Is it actually? Like if I look at it upwards, yes, it's anti-clockwise. It will look like that. So like this direction, which is anti-clockwise, which looks like C is the answer. I hope that's correct. I might have done too quick, but yeah, that looks correct. Question 13. The diagram below shows a simple generator made from a loop of wire, a commutator, and magnet. A mechanical energy source rotates the loop smoothly. The magnetic field is consistent and uniform. The output is displayed with an oscilloscope. Whichever one best describes the output that will be observed in this oscilloscope? Easy. Well, it's just a normal generator, but you have a split ring commutator, which means that the voltages are going to be rectified. Those negative voltages are going to be rectified. So you would have this basically. You would see this in the oscilloscope basically. You would have this. Like these here, and just duplicate basically. Just these ones over here like that. It'll look like this. So yeah, this is DC voltage with varying value. So it is DC. Remember, it is DC. So it's not AC, of course. But so with varying value or a constant value? No, it's not a constant value. A constant value will look like this. So there's two kind of DCs that, if you don't know, there's this DC over here which is constant. You can see. But we also have DC that's also rectified, that also changes. You can see how it changes. So it's a varying value. It changes the value, of course. The voltage is varying, of course, in terms of V. So what is this? Question 13a. Okay. Hope that's correct. 14. A rocket passes a space station at a horizontal speed of this, parallel to the side of the space station. There is a circular window on the space station as shown in the diagram. Okay. A person inside the passing rocket observes and measures the window of the space station, which the following statement best describes the measurements taken on the window of the space station. Both the horizontal and vertical measurement will be less. Okay, first let's wait. So this guy, the direction of rocket, this guy's traveling at such high speeds, so he's going to basically be observing length contraction and also proper time. And the person in the window of the space station is going to be measuring your proper length and your so let me write that, proper length and your time dilated if a person's next to the window. But we're talking, so a person inside the passing space rocket, so the per rocket, observes and measures the window of the space station. Which of the following statements best describes the measurements taken of the window? Easy. Well, what's going to happen is, because he's measuring left contraction, he's going to look at this window, because can you see how this is the horizontal part? This is parallel to the direction of motion, meaning that this part here, the person that inside that rocket is going to measure this length here be contracted. So this length here would look like this. That's not the best. Like that, like an oval actually. Yeah, like think of it like this basically. It's not the most nicest. Come on, like that. It's like this basically. So you can see this would be contracted, but guess what? The vertical. Remember, the only thing that gets contracted is what's parallel to the direction of motion. The vertical distance doesn't actually change in the window. So that's what it will look like. Both the horizontal and vertical measurement will be less. Nope. Both the horizontal and vertical will be the same. Nope. The horizontal measurements will be the horizontal measurement will be the same. No. It has to be D. The horizontal measurements will be less, absolutely, but the vertical will be the same as the actual window. Absolutely easy, nice question there. Question 15. At the Australian synchrotron, electrons are accelerated to close the speed of light by a linear accelerator. Consider electrons that enter the Australian synchrotron booster ring with a Lorentz factor which is 200, and as a result of further acceleration, in that ring reaches a much more higher level with a Lorentz factor of 2000. Which of the following best describes the effect of the booster ring on each of the electron speed and energy? Well, let's actually think about it. So we're talking about speed. So if you don't know this here, let's have a draw of the so you remember this is speed, velocity, and remember this is your Lorentz factor, if you don't know this graph. Well, we know that there's an asymptote at C, by the way. There's an asymptote at the value of C, and we know that the graph, of course, is 1, and it goes like this. Yep, and it's like this hyperbola thing. So, as you get closer, because you know how his Lorentz factor is so high, it's actually so high, like, it's so high, it means his values, it's not the most kind of best thing I've drawn, but, let's say, so which of them best describes, so in terms of the speed, it increases by a large amount or a small amount? it will decrease by a small amount, because remember, so let's say this is 200, yeah? Actually, like I kind of really, let's say yeah, this is 200, and it's right over here, and that's the speed somewhere around here. But then here it's like, because remember it's an asymptotic behavior, so it's actually growing larger and larger. Like if you don't know, it's going larger and larger. But so around here, it's around, let's say this is the 200 part. It wouldn't be like, so like it would be around here somewhere. I'm making up these values, but remember there wouldn't be a much difference. So like it would be somewhere around here. So there'll be like a small increase in velocity, not a really large increase in terms of Lorentz factor. Because remember there's this asymptote that's kind of blocking it, and so yeah, you wouldn't. So in terms of energy, it just only decreases by a small amount, you would say. And you can actually also do some calculations if you want to check that. You can kind of really do that. So if you don't remember, if I look at my where is it, my summary sheet? Where is my summary sheet? Where is it? Here it is. We can actually calculate the velocity, if you're also wondering. Remember, velocity is just the c 1 minus 1 over gamma squared. So your Lorentz factor. So let's try let's find the velocity for, what do you call it, when it's 200, your Lorentz factor. So speed of light, so times 10 to the power of a, times the square root of 1 minus 1 over 200 squared. Oh, no, sorry, I put 200. 200 squared. So that gives me a speed of 2.9, sorry, not 2 point, so basically 299996250. Whereas if you do, that's of course where the gamma is 200. But if we do the same, but now we do 2000, it's actually just 2999999. Oh my god, 9. So 1, 2, 3, 4, 625.5. That's when it's 2000. And you can really see that it really isn't a big difference. It's only a little increase in terms of speed. So that's what I mean. It's actually a little increase in speed. The electrons, speed increases by a small amount. And what about energy? And its energy increases by a large amount or small amount? Well, okay, we know energy is what? We know, your EK in terms of energy is gamma minus 1 over mc squared. Yep. I mean, you can look at this, or your total, or E total, actually. I think total energy, you would say, is mc squared. So overall, any of these would work. But basically, if you have a higher Lorentz factor, you have a higher energy. Now, because remember, the Lorentz factor is like basically times by 10. So it's actually higher. The increase in energy is going to be by a large amount in terms of energy. It will be by a large amount. So 15b. 16. Let's have a try this one. Diagram P below shows 5 energy levels of an atom with 5 transition indicated. Diagram Q shows 4 possible sets of spectral lines. Okay, so these ones over here. Whichever following frequency spectra shown in diagram Q best corresponds to the transitions in diagram P. This is quite hard because normally they'll give you these values and you would easily understand. Okay, let's look at it. Remember, this is frequency. This is in terms of frequency. So looking at the first one over here, this here has the smallest energy. Can you see how it releases the smallest amount of energy? Wow, that's a little bit hard. This here releases the smallest amount of energy, yeah? So imagine, let's assume that these are they are uniform, basically. Like, for example, let's say this was they are uniform. So can you see how this here would release the smallest amount of energy? And remember, frequency is related to energy. So if you have small energy, you have low frequency. So if this here would be the low frequency part, which would be the lowest one. Oh, they all have the same low one. So let me just draw a line right here. That's the low one. And they also have the highest one, also constant too. So that's actually really helpful. So this one here that releases the highest energy, it's also would also be the highest frequency, which is also here. So these are constant. Okay. So the other values are different. So let's assume they are constant. Let's look at the first one. This one over here, if I let's say double this here, it's like double. It's close to double. It's around double. Actually, let me make it more nicer. What am I going to do here? Because it's a little bit hard in terms of how you would... Yeah, what I'm going to do, actually, I'm going to do this, actually. I'm going to actually find the kind of distance between these two. So if I take the smallest and the largest, how much is this? That's 1. It goes 1, 2, 3, close to 3, 4, and it's 4.5. So around 4.5. So if I know that, I know this distance here, from here to here, the distance between them it has to be around 4.5. So if I kind of measure like, imagine, let's say that's 1, that's 2, that's 3, that's 4, and that's 4.5 around here. So that's 4.5, let's say, yeah. That makes it so much easier to kind of look at it like that. So if I take this over here, and let's look at the second one. So this one releases the one here. It's like double, yeah, it's like double. So think of it as this one over here would be 2 times. So yeah, so it'll be, yeah, there it is. It's 2 right here. It's this one. So the possible answers here are, it's not C, of course, because you have this extra one there. And it's not also B. It's not also A, because there's this extra one here. And let's just double check all of them. So what about this one over here? So this one over here is what? Like, it's basically, if I take this one again, it's 1, 2, 3, like 3.5 basically. So 3.5, so if that's 1 here, that's 2 and 3. What the hell is this? Wait. I think I'm overthinking. This is actually really hard because you're trying to like break the question down. Wait. So, no, it can't make sense. So wait. If I take, so I've already done that one. The next one here, take this one. I'm gonna just, yeah, let's duplicate it. So like that's 1, that's 2, that's 3. Yeah, 3.5. So which is 1, 2, 3. 3.5 should be around. Yeah, it looks like it's D. No, it does. D looks the most fitting in all of them, to be honest. I don't see it over here, but let's try the next one. This is actually a little bit harder. So what about this one here? This one actually looks like the difference is just that 0.5. So it's actually really high. So, yep, that makes sense. That's 1, 2, 3, 4. So, sorry. That's 1, 2, 3, 4, 4.5, around there. And yet you can see that there's an actual peak on that one. So that here would correspond to this one over here. And then, yep, this one here, there's only this little bit small increase. So I think it's like 1. The difference is 1. Which, yep, you would see that one there. This overall 1 here kind of corresponds to all of it. Like, so looks like D would be the best in that. That's actually hard, man. Like, really, really disgustingly hard. Like, no, just not normal to put a question like this. Just put some values, make it easier. Like, this one's just, I don't know if it's even D, to be honest. I just assumed in terms of these, like, D looks like it's most fitting. Oh my god. So 1, 2. See oh my god, that's actually a little bit. Yeah, it's like it's really not even that good, this whole question. Yeah, I don't know. I would assume D, because D fits most of the stuff. This one's actually taking longer than I expect. D looks like would be kind of, so it fits, okay, I understand that one, understand that one, understand that one, understand that one. Then this one over here, this part over here, it's like twice. So wouldn't it become 1, 2? Wouldn't it be over here, which only like close to this one that would have it? No, but D fits most of them, so I would assume it's D. Yeah, I want to look at this again maybe next time. So D, I would assume that D. So 16 is D. Yeah. All right. Questions of D. The diagram below shows a standing wave on a stretched string between 2 fixed ends at t equals 0. The frequency of vibration of this, okay, which will follow best diagram correctly shows the position of the string at t equals that. So, okay, that's actually easy. Well, we can actually, because we know the frequency, we can find the period. So 1 over frequency, which is 1 over 50, which is what? So what's the frequency? 1 over 50? That's basically 0.02. Okay, seconds. So basically, if you remember, what does period mean? It's actually the time, how long it takes to move for a cycle like this. Can you see how that's one cycle? So overall here. So imagine like, so it takes 0.1 seconds, so it will take 0.2 seconds to move from here all the way for the next cycle, like that. But we're only saying which of the form best correctly shows the position of the string at t equals that. So basically half the time. So imagine, it's right over here. It'll move over here. So basically this is what it will look like. And so in like half of that time, it will look like this, the red one, which looks like B. 17B, that looks not too bad. Yeah. Question 18. An interference pattern produced by a monochromatic light is viewed on a screen placed at a distance L from a double slit system with a slit separation D. The distance between the centers of the 2 adjacent bright bands is that. The distance L is doubled and the slit separation is halved. Which of the following is closer to the new distance between the centers of the 2 adjacent bright bands? Really beautiful question. So change in X is lambda L over D. So what we're doing is we're doubling L. So if you double it, you put a 2 there. And you're halving the split separation. So this D becomes D over 2. Now, if you don't know fractions, so basically what's going to happen is this 2 kind of, you can bring that 2 on top here. So 2 times 2 will be 4. Which is basically, if you think about it, it's just, it's like, it's basically 4 times your change in X. So choose D, so 18D. Is that? Yep, 18D, it looks like it. Question 19. An orbital velocity v of a satellite in orbit r around the planet of m is given by this. Which of the following is a linear graph that's consistent with this relationship? No. V, and if you're going to graph v and r, it's like this. It's a square root and a hyperbola, so it's absolutely not that. Nope. B, so yep, v squared. So imagine you square that, will be then, if you're squaring it, this whole thing will, the square root will disappear. But if you're graphing with r, it will actually look like a hyperbola. So it will look like, it would look, sorry, hyper looks like that. So it will look like this, basically. Like that. That's wrong. It's not linear. So that's also wrong. C, so again, that's also wrong because you need to actually square that velocity. Because say you, you graph, you're basically graphing this. So imagine that gm is a constant. So it's m over 1 over x. Yeah, it's going to be like a, 1 over r, which is basically like x. It's basically going to be like a square root graph. It'll look like this then. So it has to be D. And yeah, D makes absolute sense. Let's make sense of D. Well, D, what you're going to do is they square rooted V, which now you get this, gm over r. And what they've done is that 1 over r, they took it out, like that. So imagine, okay, V squared, imagine that's your Y value. That's your X value. So let's replace them. So that's going to be your Y. Gm is a constant. Let's call it M. And 1r is X. So can you see how it's a straight line? It's a straight line equation, so it's D. Question 20. Data can be described as precise when? Remember, precision is what? Precision is how close are the values together. If they are very close together, then they are really precise. It is the result of a careful investigation. Nope. The experiment is repeated many times. Yeah, so precise. The more you repeat it, yep, there's more. The more likely you'll decrease that random error, and then they are more precise. And the results show little absolutely show little variations. You need to have the range between them has to be small. B is actually the definition of it. The same experimental methodology used. Nope. It is close to the scientifically accepted value. This is like the, I think that's, they mean here is not precise but accurate. So B, 20B. And yeah, guys, I hope you enjoyed this video. You can check your answers through this. I hope I got all of them right. This one is a little bit, where is it? If you just see any little mistake, this one here is a little bit hard, I'm not gonna lie. So I probably got that one wrong. I need to look at it again. And yeah, I hope this video helps you out, and good luck. Good job. Congratulations on finishing physics forever. Bye-bye.